Episode 7, Best Representation. Let's recap the problem statement. A string is a non-trivial power if it is, some other string in the power of k for k at least 2. Here, power k means concatenation of k copies. A string is good if and only if it is not a non-trivial power. We are given a string s. We want to split it into the smallest number of good parts. So we cut it in some places. So all the parts will be non-intersecting subsegments that cover all the string. And also we want to calculate the number of possible splits with minimum number of parts. And the string is very long, up to 500,000. Here on the left, some examples of powers, non-powers that are good strings, and optimal splits for some strings. Let's first deal with some special cases. A string that consists of k copies of the same character can be good if and only if k is equal to 1. So this string should have length 1. So if our given string is n copies of the same character, any its substring that is good must have length 1, because it will also consist of equal characters. Therefore, we have to split it into n substrings of length 1. That's the only way to produce a good split. So the answer is minimum number of parts is n, and there is only one way to do that. If S is good itself, then minimum number of parts we can have is 1, and there is obviously only one way to do that. So we'll need to check if S is good. We'll see how to do that when we will discuss how to solve the problem in the general case. So the general case is S is not n copies of the same symbol, but S is not good itself. So S is a non-trivial power. And the main idea of this problem is that we can always do with two parts. In this case, specifically, we can always cut off the last symbol of the string, and that suffix of length 1 is obviously good. And we can prove that prefix of length n-1 is also good. It cannot be a non-trivial power. To prove that, we will use a very nice and very important result from stringology. If a string of length n has periods p and q such that p plus q minus their GCD is at most n, then GCD of p and q is also a period of that string. So I used a word period a lot. What is a period? Number p, integer, positive, is a period of string s if and only if for all positions I, character on position I is equal to the character on position I plus p for all I for which this makes sense. Both I and I plus p should be inside the string. Note that p does not have to divide the length of s. So for example, this string on the right, AAB, AAAB, AA, it has periods of length 4, and period of length 7, and also a period of length 8. And if we could apply our theorem to this period, to periods 4 and 7, we would say that the string must have a period of length 1, but that's not true, but that's because periods 4 and 7 do not satisfy this inequality. Their GCD is 1, so 4 plus 7 minus 1 is 10, but this string has length 9, and 10 is greater than 9, so this inequality is like the best possible. If the string would be 1 longer, it couldn't have periods both 4 and 7 and not have a period 1. And we can see that to continue string having a period 7, we would have to write b here because it should be equal to this b. But to continue to have a period 4, we should write a because it has to be equal to this a for back. And we can do both. This is not a very simple result. It is kind of intuitive. Like if a string has 2 short periods, then like we can jump back and forth and like prove that characters on positions different by GCD also should be equal. But to get it with this very tight bound is not very easy, and I will give a proof, but it is not very strict. It's fine, and it provides at least an understanding of why it should be true. But to make it really strict, you'll need to do more job than I have done here. So okay, let's try to prove this theorem. Let's first try to prove it for GCD 1, so P and Q are coprime, and we also restrict ourselves to having lengths exactly P plus Q minus 1, which is GCD. So turn this inequality into equality. Let's number positions in the string from 0 to P plus Q minus 2. I was not very consistent with it here. I think that in stringology, like it is usually one indexation, but yeah, in this proof it is a bit more convenient to use zero indexation, although it is not necessary. So what does it mean to have a period? Well, by definition, it means that for any 2 positions inside the string that are on distance p, they should be equal. So we kind of can construct a graph where vertices are positions in the string and edge connect to vertices when we know that they should be equal. So we have some edges that are generated by a period P, we have some edges that are generated by period Q, and we want to basically show that this graph is connected. And thus, for any 2 positions, we can follow some path from one to another, and that will show that characters on those positions should be equal, therefore all the characters are equal, and our string has period 1. we will try to show that in this case, this graph is actually a bamboo, which is not easy to see from this picture, but it is true. And here in cyan, I try to index vertices in the order of bamboo. And we will do that by saying that let's use edges of length p as jumps right, so we will use them as plus p, go right in the string using those edges, and we will use edges generated by period q as jumps to the left, so minus q. Then because the length of our string is p plus q minus 1, we can do this plus p jumps for positions from 0 to q minus 2, and we can do minus q jumps for positions from q to p plus q minus 2. So we can see that those ranges do not intersect. Moreover, from position q minus 1, we are not able to do either of those jumps. So we will start in position p minus 1 and do the jumps, and I want to show that at the time we arrive at position q minus 1, we have visited everything using those jumps. So we have shown that this graph is a bamboo, actually. Okay, so we start in p minus 1. Let's do it first on this example. So we start here, we jump 3, 3, minus 8, 3, 3, 3, minus 8, 3, 3, and we end up at position q minus 1. So let's say that we have done x jumps plus p and y jumps minus q. We started in p minus 1, so we will arrive at position p minus 1 plus x times p minus y times q. Each plus p jumps changes the remainder modulo q, but doesn't change the remainder modulo p. Similarly, each jump minus q changes the remainder modulo p, but doesn't change the remainder modulo q. And because p and q are coprime, since we only change the remainder modulo q by doing plus p jumps, we have to do q of them to return to the same remainder modulo q we started with. And the same for q jumps. We have to do p of them to return to the same remainder modulo p. Let's see what should be x and y for us to arrive at q minus 1, which is the only position from which we cannot continue. So until we arrive at q minus 1, we can continue always. So q minus 1 is p minus 1 plus q minus p, because I want to replace this p by q. So we would like to say that this plus q is this and minus p is this, but x and y should be non-negative. And here both of them are minus 1. So actually we will have to do q minus 1 jumps plus p and p minus 1 jumps minus q. So before stopping in position q minus 1, we will make q minus 1 plus p minus 1 jumps. Therefore we visit starting cell, and then q minus 1 plus p minus 1 jumps, we visit another cell. So in the end we will visit p plus q minus 1, which is n cells. And I want to say that those are unique cells. Why is that? Well, because as we mentioned here, we cannot go back to the same remainder modulo q without doing q jumps of plus p, and we haven't done them yet. So for two cells that we have visited during our jumping process, there were some number of plus p jumps between them, which is at most q minus 1, some number of minus q jumps, of which there was at most p minus 1. There can't be zero of both, because that would be the same position in the sequence of visited cells. So yeah, they're different. So we have proven what we wanted to prove, that in this sequence of jumps we can visit all the unique cells. The part that is not very strict is, well, I'm kind of assuming that I will end up in q minus 1, which is not very clear why. Like, I need to show that I will actually visit this cell. It shouldn't be very hard. Like, it definitely should be possible, because, well, each jump from each cell is uniquely defined, and like, we should show that the jumps we will actually do will get us to the point where we have done q minus 1 jumps plus p and p minus 1 jumps minus q. But it is like, it's not obvious. We should prove that, and I don't want to do that. So we'll say that we have hand-waved our way into proving this theorem for the case when GCD of P and Q is 1 and N is exactly P plus Q minus 1. The remaining cases are very simple. Let's first finish with GCD equal to 1. If N is strictly greater than P plus Q minus 1, we can first apply our proof for prefix of size P plus Q minus 1, and then each of the remaining symbols should be equal to the one on position minus P from it, and we have already proven that all of them are equal, so we can increase the size of the prefix for which we know that all of them are equal. And for arbitrary GCD, if GCD is 1, then we have already proven the statement. Otherwise, we cannot change the remainder modulo GCD by doing jumps plus minus p and plus minus q. So for different remainders, they're surely in different connected components, but for fixed remainder, we can look only at the positions with this remainder and like put them in their special string. Then it's easy to show that it should have periods p divided by GCD and q divided by GCD, and its length is at least the sum of those periods minus 1, so we can apply the statement from the theorem for string with GCD equal to 1, GCD of periods, and like for every remainder, thus we will prove that all the characters on positions with that reminder are equal, and that is exactly what it means to have period equal to GCD. So that finishes the proof of this very cool theorem. And well, basically what this theorem gives us is that a string cannot have like any set of periods. It can have some big periods that are longer than bigger than n over 2, but let's say that a string has a period that is smaller than n over 2. Let's take the shortest of them and call it p. Then obviously every number that is divisible by p is also a period of the string. And our statement is that there can't be other short periods. So we can have one short period p, and all the numbers that divisible by p also will be periods, but they can't be periods that are shorter than n over 2 and they're not divisible by p, because otherwise their GCD like of that period and p also should be a period. It's not exactly what's written here, but actually later we will prove a statement which like its proof can be extended to give the proof of this statement. And so like a set of periods is, well, kind of defined by the smallest period and very big periods that are close to n. So they should be like bigger than n minus the shortest period. Okay, let's go back to the problem. We have kind of proven a cool theorem. Now we should apply it to the statement we want to prove. And that statement is that prefix of length n-1 of a non-trivial power cannot be non-trivial power itself. Let's try to prove by contradiction. Suppose it can. So our initial string s was a case power for k at least 2, and the prefix of length -1 is else power for l at least 2. Then s must have a period n divided by k, let's call it p, and our prefix of length n-1 must have period n-1 divided by l, let's call it q. But obviously all periods of s are also periods of all its prefixes, if they're short enough. So prefix of length n-1 has both p and q as its periods. And we want to apply the theorem we proved. For that we need to understand, calculate GCD of p and q and look at their sum minus GCD. So GCD is 1. They must be coprime, and to show that we can understand that p is a divisor of n and q is a divisor of n-1. Specifically p times q is n and q times l is n-1. If we look at their difference, it will be 1. Therefore p and q should be coprime. Right? Like their GCD should divide 1, but that means that GCD is just 1. Now let's look at their sum. P is n divided by q by k, q is n-1 divided by l, K and L are at least 2, so this is at most n over 2, and this is at most n minus 1 over 2. So their sum is at most n minus 1 plus 1 half, but we want just n minus 1. But this is integer, obviously, so this is strictly smaller than n, therefore p plus q is strictly smaller than n, so it's at most n minus 1, which is n minus GCD. Okay, so our prefix of length n minus 1 must have a period 1, which means that it consists of the same symbol repeated n minus 1 times, but then our initial string s should also have the last character equal to that c, because it is a non-trivial power, and that is a special case that we specifically not included in this theorem. Otherwise, the number of parts is 2. And otherwise means that S is not a repetition of the same character n times, and S is a non-trivial power itself. Okay, so now we know that we are only interested in splits in 2 parts, so it will be prefix and suffix, and there is at most, exactly n minus 1 possible splits. So let's just check each one of them to calculate their number. So you can remember that you asked to calculate the number of minimum splits modulo something, but it is actually at most n minus 1 always. So now we want to check for each prefix and suffix whether they are good, which means that they're not a non-trivial power. Let's check if each prefix and suffix is a non-trivial power. Solution for suffixes is just solution for prefixes on reverse string, because if string is a non-trivial power, and if and only if it's reversed is a non-trivial power. So we need to understand how to solve for prefixes, then we will reverse the string and apply the same solution to get the answer for suffixes, and then we will just check for each split whether it's good. And that also includes the solution for checking if the whole string is a non-trivial power or not, because it is its own prefix, so we will understand for it too whether it is a non-trivial power or not. Okay, let's just check each prefix. Potential power, the number k, should divide the length. So let's iterate over divisors of length. So we have fixed length and k should divide length, and we want to check whether prefix of this length is a case power of something. Obviously it should be a case power of its own prefix of length, length divided by k, it's called p, and then we want to check that if we cut this prefix into k parts of length p each, and so on, this k strings here, they all should be equal. That's a lot of checks to do, but we can actually concatenate all of the strings except the last one, and concatenate all the strings except the first one, and check that they're equal. So we get like this. If we do the checks stupidly, then it doesn't help us at all. The number of checking the two positions are equal is still the same, but now we just want to check if two substrings of a given string are equal. And we can do that with hashes, but actually the first one is always a prefix, so we can use that function instead. If we calculate that function for the whole string, then to check if this is true, we should look at that function that for position which is the first position of this second string, and that function by definition for each such position will calculate what is the longest common prefix of like suffix starting from this position and the whole string. So we should just compare whether that LCP is at least len minus p or not. Okay, so what is the complexity of this solution? Well, if we iterate over pairs length and k, where k divides length in a smart way, which is iterate over k first and then iterate over length that is divisible by k as k times x for integer x. For fixed k, x should be at most n divided by k, so the number of pairs we'll check is calculated like that, and you should, which says must, know that the sum is of n log n, because it is of n times sum of 1 over k up to n, and that is partial sum of harmonic series, and it is probably the second most important thing in competitive programming after binary search, that the sum of harmonic series, the partial sum up to n, is of log n. It is used to calculate the complexity in many cases. So the number of pairs to check is of n log n. Each check is constant time, whether with hashes or with that function, and also we need linear time to prepare either that function or hashes. So that's great, and that gets accepted. But actually we can do a bit better. So a border of a string is a non-trivial suffix that is equal to a prefix of the same string. Obviously, we should take suffix and prefix of the same length, otherwise they're surely not equal. So, like, border should be just a number, but if I'm not mistaken, in stringology, border is a string, so border is a suffix. But yeah, all the borders of the string are defined just by like for each length we should say whether it is a border or not. And borders and prefix and periods are actually very close connected in a sense that they are basically interchangeable, which says the statement of this lemma: string of length n has period p if and only if it has a border of length n minus p. And the proof of this lemma is just to look and see that in both cases we check this equality of strings. So in both cases we actually checking that all the characters on positions that are different by p are equal. That's just the definition of what does it mean to have a period p, but also that's what border of length n minus p gives us. Okay, and now using these borders, we want to devise just a check that a string is a non-trivial power. And let's say that b is the length of the longest border of S. Here we say non-trivial suffix, so the suffix that is not equal to the whole string. Uh, for uh, for the purposes of the definitions working in the same way, we should just agree on whether border can be empty, so we can have a border of 0 length, and whether a period of n or even greater than that is valid. And I think that the simpler condition is to say yes to both of those questions. So a string can have a period of a period n, and the corresponding border is an empty border. A string always have some borders, for example empty border. Let b be the length of the longest border of S. Then we know that n minus b is a period, and therefore it should be the smallest period. And if we have a smaller period, then it would correspond to a longer border. And we want to prove that S is a non-trivial power if and only if b is greater than 0 and n minus b divides n. The right to left direction is obvious. Just n. So S is a power of its own prefix of length n minus b. We know that n minus b is a period, and since it divides n in strictly smaller than n divided by n minus b equal to k is the exponent for which S is a k's power of its own prefix of length n minus b. So left to right direction is a bit harder, and again it uses the theorem we proved earlier. So suppose S is k's power for some number k which is at least 2. We want to prove these conditions. So p which is n divided by k must be a period of S. But n minus b is also a period of S, and we know that it is the smallest period of S. So either p is equal to n minus b, and then we understand that p divides n, so n minus b divides n, and b is greater than 0. Or p should be strictly greater than n minus b. Okay, then p and n minus b are both periods, and they're both at most n over 2, because p should divide n and b is strictly less than n, so it's at most n over 2, and this one is even smaller than that. And yeah, here we will prove that that means that their GCD is also a period. And this proof actually just works well. N minus b will be just like a number. So if we have two periods that are both at most n over 2, this works. So how do we show that? Let's look at their sum. I want to state that n minus b is at most p minus GCD of p and n minus b. Why is that true? Because, we know that n minus b is strictly smaller than p, so if we look at their difference, it should be divisible by their GCD, so their difference should be at least their GCD, so n minus b is at most p minus GCD. And from here we understand that p plus p minus g, that's how we will call GCD, that's the value, and 2p is at most n. So the sum of periods is at most n minus GCD. Therefore, G is a period of S. But G is a GCD of n minus b and something, therefore it can be bigger than it, but also n minus b should be the smallest period. So we get that G is at most n minus b, but G should be at least n minus b. Therefore, they are equal. So n minus b, which is actually G, divides p, because it is GCD of p and something else, and p divides n. So we get that n minus b divides n, and obviously b is non-zero. So we have proven the lemma. So now if we can calculate the longest border, the length of the longest border for each prefix of S, we will solve the problem. That is the definition of prefix function. Prefix function, or p function, calculates the length of the longest border for every prefix of the given string in linear time. So you calculate prefix function, and then you can check every prefix, whether it is non-trivial power or not, in constant time, thus getting you a linear solution to the problem. That's it for episode 7. Thanks for watching.